Morning. So we continue our minimum maximum principle. As I said, we will be proving just one result, and that's all in the setup of this one. So we are going to write for the Neumann case similar Dirichlet case and such similar results. There are results you can look into many other PDE books like Gilbert Rodinger and many other books into that one. So maximum principle or minimum principle for weak solutions. Okay. Okay. So you assume Aij is elliptic. This we are assume. So we are writing it assume Aj is elliptic. Okay. And the minimum things assume you always need that A naught L infinity and A naught of x greater than or equal to 0. So write weak maximum principle. Okay. Let omega bounded, open, smooth, whatever smoothness you need according to the requirement. Okay, smooth, and f is in L2 of omega and u belongs to H1 of omega intersection C omega bar satisfies integral of Aij of x du by dxj dphi by dxi plus integral of A naught of x u v, this is in omega, this is in omega, is equal to integral of f of v for all v in H1 naught of omega. Then 1 f greater than or equal to 0 in omega, u greater than or equal to 0 on gamma, that is a boundary, implies u greater than or equal to 0 in omega. 2, that is 1 is the one only you want to prove. If A not equal to 0, f greater than or equal to 0, that implies implies u greater than or equal to 0 greater than or equal to infimum of u over gamma in omega. So let me write that one. And 3, further if A not equal to 0, f equal to 0 implies infimum of u over gamma less than or equal to u of x less than or equal to supremum of u over gamma. Okay, this is true for all x in omega. Okay, so let me give you a proof of this. Is that clear? So this is the one, the rest are all deductions. So this is the only one you have to prove it about the weak maximum principles. Okay, so these conditions f and the thing u on the boundary gives you u greater than or equal to 0. So the proof, we recall one of the results which we have simple results you are study If u omega smooth, of course you are assuming u is in h1 of omega, we have derived that u mod u plus u minus in h1 of omega. Okay. So, you have recall that results. So, 1 the proof, if u greater than or equal to 0 on gamma, that implies u equal to mod u on gamma. So, and that implies your u minus, there is no but u minus is in h1 naught of omega. That is the thing you can conclude, because there is nothing that by trace u minus will be on h1 naught of omega. So, therefore, that implies in the weak formulation, where is the weak formulation? This is the weak formulation. Weak formulation star, you can take V to be u minus, can take V equal to u minus, and u minus and u plus have u minus u plus essentially in the sense that we have disjoint support. Okay. Essentially have disjoint support, in the sense that if at all they coincide, it will coincide only on a set of measure 0, essentially have disjoint supports. So, that implies in the weak formulation because you also recall u is equal to u plus minus u minus, use that. So, the u minus part will go and you will get aij into u plus part will go, because it has a disjoint support, this du minus by dxj. Here you have to write u plus minus u minus, that is a sign coming here, and u plus part will go because of here I am taking v equal to u minus, which is allowed because it has that one, minus integral of a naught of u minus whole square equal to integral of f u minus, okay. That of course is greater than or equal to 0, u minus is always positive. So, you have this one. Okay. Now, use ellipticity. So, that exactly meaning you reverse that one, integral of aij, this is let me use the comfortable notation, di of u minus plus integral of a naught of u minus square is less than or equal to 0. So, use ellipticity. So, this portion is greater than or equal to alpha into integral of grade u minus square, okay, and both are positive. So, this immediately implies your u minus equal to 0 almost everywhere, and that implies your u equal to u plus, which is greater than or equal to 0 almost everywhere. So, the proof is just realizing this fact, nothing more than that on that one. Okay. Yes. Okay. So, the second parts are trivial. 2. If a naught equal to 0, identically 0, and let m is equal to infimum of u over gamma, and then you see you can add a constant. That implies if a naught identically equal to 0, you put let is equal to m, a naught identically 0, then you can add a constant, because you look at this weak formulation and adding a constant will not change. So, if you use a solution, you can add any constants here u, that is what you will get it. So, that implies u minus m satisfies star. And u is the infimum and u minus m is greater than or equal to 0 by 1 by the first part. Okay. That is what exactly you want to prove in the conclusion, you see, u greater than or equal to 0. So, you apply for that u minus 1, and 3 is for the further if m f equal to 0 as well, then minus u also satisfies star, also satisfies star, okay, and hence 3 follow, that implies 3. You can apply for minus 3 u, that will become the supremum of things to be proved. So, we will discuss another important thing, what is called the eigenvalue problem. So, I will begin with this today, and then we discuss more tomorrow. Okay. Eigenvalue problem. So, you see, so this is connected with your resolvent etc. You will be seeing later more details about the resolvent, the solvability of that eigenvalue problems. You will see more detailed analysis, you will be seeing it in the course when you study evolution equations etc. So, we are restricting only to the eigenvalue problem corresponding to Laplacian, that is all, corresponding to Laplacian. So, these are all various issues regarding just about your second order operator, you see, and lot of literature here. So, how does a eigenvalue problem looks like? So, you have your operator minus Laplacian, u equal to lambda u. So, that is how you look at, recall when you have a matrix A. So, looking the solvability is about A x equal to b, but so what is the eigenvalue problem? Looking for lambda complex numbers such that A x equal to lambda x, and of course, it should be there x is x not equal to 0. So, same thing, this is in Rn analysis, and whenever such a lambda is called an eigenvalue and x is called an eigenvector. The problem is that when you go to infinite dimensional setup, is not only the eigenvalues which you will find out, you will have the so called other spectral values, and when you study unbounded operators, minus Laplacian is an unbounded operator. When you have an unbounded operator, you can have continuous spectrum, residual spectrum etc., and complement of all that is what your resolvent, and there is an operator associated. It is not only that you are the it is all thing, and you also want to understand the boundedness of this inverse, which is not obvious, but in finite dimensional situation you have only eigenvalues. The moment you have an eigenvalue and you know all that, you know about the related to its solvability and all of that, and inverse, the moment you have an A has an inverse, whatever it is, a lambda has an inverse, that immediately it is a matrix and it is automatically bounded linear operator. So, such things are there, but that is not true when you go to infinite dimension. So, the infinite dimensional operators which are closest to this finite dimensional version are compact operators, and you have a very general spectrum of analysis, spectral analysis of compact operators, and that you have essentially eigenvalues, a possible converging point as 0. So, that is a very general thing in functional analysis. So, look functional analysis books on spectral analysis of compact, spectral theorem of compact operators, theorem of compact operators. Interestingly, our Laplacian, we call it operator in the sense that we are going to define, which you have already seen, minus Laplacian inverse is compact. You will see that it is essentially solution operator is compact. Solution operator is invertibility. You have to understand all that phenomena. Okay, solution operators, operator is compact in appropriate spaces. When you say that, so this is what you are going to study. We will discuss it soon. We will have, so we will come to that later. So, let me make these remarks which you are doing it. So, when you are solving this equation, maybe I will tell soon properly in the next page. So, that is what essentially you have to understand. So, understanding this is a compact, and this gives you eventually only eigenvalues, and that too a discrete set of eigenvalues. That is very crucial. So, you see, for a matrix you have an exactly n eigenvalues may be counted up to multiplicity, because same eigenvalues can give different eigenvectors, but that is not the case when you go to infinite dimension. There are operators which can have no eigenvalues at all. So, okay. So your job is to find lambda. You see, I am just replacing your lambda u by f by lambda u, but that is different. So, find lambda and u. Of course, lambda is real. Now, real you will prove it because of the self adjoint. In general, it need not be, and your solution will be in H1 naught. So, you can give a variational formulation. So, but lambda u are unknowns. That is what you have to understand. Okay, this is unknowns. Okay, all right. So, let me try to understand this one. Of course, as I said, one can consider. So, I will you can follow a similar argument. One can also consider, see, as long as the second order operator elliptic with a non-negative first order term, there is no issue. The same procedure can be adapted. A j of x du by dx j plus a naught of u equal to lambda u. So, in omega and u equal to 0 d omega. For the simplicity, I will work with the Laplacian. Okay. Here a naught of course is greater than or equal to 0. Then only you know that the solution, unique solution operator you can define, which we have seen it in our weak formulation. Okay. So, we and you need elliptic, aj elliptic, you need that as well. Elliptic, elliptic means we are only considering uniformly elliptic, we are not considering any degenerate equations. Okay. So, yeah, one remark immediately is that if lambda equal to 0, you see, it immediately implies. So, I am considering one, okay, considering Laplacian. Is true here also, considering minus Laplacian only. Okay, that does not matter even if lambda equal to 0 by uniqueness, then it is a problem. This one, you see, then once you fix lambda, it is a standard solution operator problem in omega, and u equal to 0 on d omega. So, by uniqueness u identically 0, that implies lambda is not an eigenvalue. So, I did not define. If there is something you can do here, this lambda is called an eigenvalue if x is eigenvalue, and u is called eigenvector, corresponding eigenvector. So, same terminology. Okay, if you do that. So, lambda is not an eigenvalue. So, that is immediate. You need u non identically 0, not an eigenvalue. Yeah, these are all maybe I am taking for granted of the u not identically 0. You need that. Then only you call it an eigenvalue. Okay. That is one point. And if lambda not equal to 0, u not identically 0, then lambda is an eigenvalue and corresponding eigenvector. Now, you understand this solution operator. During the study of our Fredholm alternative, we have studied this in detail. So, let me describe this solution operator. So, let us try to understand that. So, you have your f in L2 of omega. Okay. So, let me do this here, and then consider Laplacian u equal to f in omega. This is the problem. So, u equal to 0 on d omega. This is your standard problem. It is not an eigenvalue problem. So, that gives you unique u. I call this to be g of f, and this we have seen it. So, what and or let me not use u. So, let me call it w. W equal to g f. This is in h1 naught. And what is the weak formulation? Integral of gradient of g f, gradient of v equal to integral of f v. We have discussed this plenty of times. So, you should be comfortable by now. If not, what to do? I am sure you should go back if you are not yet comfortable. So, that gives you, it is the same procedure. We have done it many times. We have done it many times with because that will be repeatedly coming. So, you have a g from L2 to H1 naught. Okay. So, f going to, and repeatedly doing it, because if you are learning it for the first time, you may take time to grasp these ideas. Okay. So, g f equal to w. Okay. And this is your solution operator, but then I treat it in a different way, and the continuity tells you that this operator g is, of course, g is linear, continuous. Okay. And continuity means this is what you are using it now. You see your g f in h1 naught is less than or equal to constant into norm in L2 of omega, very clear. But now you see the embedding that h1 naught of omega, the identity map to L2, this identity is compact. So, you can view your G as I composition G as a mapping from L2 to L2. So, you view your solution u going f going to w equal to g f in as an element in L2 and is compact in this way. So, the solution operator when you view it from L2 to L2 is compact, that is what you are. Okay. So, you have a compact operator. So, this is precisely in symbolically, if you look at it, probably you may not have seen it, symbolically G is your minus Laplacian inverse with that eigenvalue problem. That is what you have to understand, that is what you are getting as compact, you see, because it is a G. So, this is what you are trying to do it, minus Laplacian of u equal to f, of course with condition, that is a boundary condition is what added there, and u is equal to minus w. W and you have your W is so W is equal to minus, with that boundary condition you have to solve that one, then only you get well definedness of the uniqueness of that, you see. So, this is a kind of a, if you want, that is also a symbolic representation. And one more quick comment and then I will stop it. So, I will continue this for, so get familiarized before reading the before listening to this lecture thing. F and G of L omega we get. So, I will tell. So, first property is about the compactness. So, we get integral of so you take V equal to G. So, you get that one. So, if you have your grade GF, okay, so grade GF, and then you have your grade V, that V to be taken, V is in H1 of omega. So, take V is equal to GG, you can do, because it is in H1 naught. So, when you do that one, you get your GG, that is nothing but integral of F GG, but this is symmetric. So, you can reverse the role of F and G. So, you can also by reversing the role of F and G, this is also equal to GF. So, you see you have that one. So, that essentially implies what is FGG is equal to GFF. So, that means FGG, this is an L2, everything you view it as an L2 is equal to GFG, and you get it to be the G is symmetric, okay, symmetric we call it. Of course, there will be when you deal with the unbounded operator have that, but here it is everything is perfect and you have G is self adjoint. So, you see. So, what you have is that in conclusion G is a symmetric compact. Symmetry immediately tell you your eigenvalues will be real. Symmetric compact. Symmetric means self adjoint, you will have here self adjoint compact operator, and you know the spectrum of that one, which I will discuss it next time. So, your operator, the solution operator which are defined is in a good shape corresponding to your Laplacian. So, that is what we have proved. So, we continue this one. Now, you know how the spectrum looks like that, and then we give some characterization via Rayleigh quotient, all that in the next lecture we will do that. So, we will have couple of lectures in this direction, and after that we will be moving on to the evolution equations. So far will be all is elliptic equations, you will see more on the evolution equations. Thank you very much.